The Milky Way has been making planets for over 10 billion years. By conservative estimates, there are at least 100 billion Earth-like worlds in our galaxy alone. Many of them are older than Earth by billions of years. If even a tiny fraction ever birthed technological civilizations, some should have had a head start of tens or hundreds of millions of years. That's enough time to cross the entire galaxy, many times. And yet, when we listen, we hear nothing. No star-spanning empires, no obvious megastructures. This is the Fermi Paradox. By the numbers, the universe should be teeming with neighbors. So where is everybody? The Fermi Paradox is named after physicist Enrico Fermi, who supposedly asked over lunch in 1950, "Where is everybody?" It's the clash between two ideas. First, the universe is huge, old, and full of planets. Second, we see no clear evidence of advanced extraterrestrial life. Both statements seem true. Together, they don't fit. To understand the paradox, you need a sense of scale. The Milky Way is about 100,000 light-years across, with roughly 100 to 400 billion stars. Many are orbited by planets in the habitable zone, where liquid water could exist. Our galaxy is over 13 billion years old. Earth formed only 4.5 billion years ago. If intelligent life is not absurdly rare, it had enormous time and space to arise before us. The classic way to think about this is the Drake equation. It's not a precise formula, but a framework. It multiplies several factors: how often stars form, how many have planets, how many of those planets are habitable, how often life appears, how often life becomes intelligent, how often intelligence becomes technological, and how long such civilizations last. We now know some of those numbers fairly well. Space telescopes like Kepler and TESS show that planets are common. There may be more planets than stars. Perhaps 1 in 5 Sun-like stars has a roughly Earth-sized planet in the habitable zone. That alone suggests tens of billions of potentially habitable worlds in the Milky Way. But the crucial terms, the probability of life, intelligence, and long-lived civilizations, are almost completely unknown. Depending on what you plug in, the Drake equation predicts either a lonely galaxy or a crowded one. The paradox becomes sharp when you consider expansion. Imagine a civilization that masters interstellar travel even slowly. If they can send self-replicating probes or colony ships at just 1% the speed of light, about 3,000 kilometers per second, they could cross the galaxy in about 10 million years. That's a blink compared to the galaxy's age. Even if expansion is much slower or happens in fits and starts, a single ambitious species could, in principle, fill the Milky Way with settlements, machines, or at least detectable engineering in under 1 billion years. Not every civilization would choose to do this. But if even 1 in 1,000,000 did, and if civilizations arise frequently, the galaxy should already be visibly altered. We should see stars dimmed by megastructures, waste heat from vast industries, or at least unambiguous artificial signals. Instead, our telescopes reveal a cosmos that looks natural. So what could resolve this tension? One family of ideas says, we're early. Maybe complex life is intrinsically unlikely and takes a long time to appear. Some researchers suggest that the universe only recently became friendly to life, as heavy elements from earlier generations of stars accumulated. In this view, Earth might be among the first wave of intelligent species. Another possibility is the Great Filter. Somewhere between dead rock and galaxy-spanning civilization, there are steps that are extremely improbable or extremely deadly. The filter might be behind us. Perhaps the origin of life, or the jump from simple cells to complex ones, is vanishingly rare. That would mean intelligent civilizations are almost never born. Or the filter could lie ahead. Technological societies might almost always destroy themselves through nuclear war, runaway climate change, engineered pandemics, or something we haven't imagined before they spread to the stars. If that's true, the silence is a warning, not a comfort. Other ideas shift the blame to our expectations. Maybe advanced civilizations don't build loud, wasteful empires. They might go inward, focusing on virtual realities, ultra-efficient computation, or minimal energy lifestyles that are hard to distinguish from natural processes. This is sometimes called the estivation hypothesis. Advanced beings could be waiting for the universe to cool, when physics allows more computation per unit of energy. Or perhaps we're simply not looking correctly. Our searches for radio signals, SETI, have sampled only a tiny fraction of the cosmic haystack. All frequencies, directions, times, and signal types. It's like dipping a cup into the ocean and concluding there are no fish. Civilizations might use communication methods we barely understand. Neutrino beams, tight laser pulses, or exotic quantum channels. They might broadcast rarely or only locally. The universe could be full of quiet, modest civilizations that never shout loudly enough for us to hear across thousands of light years. Then there's the unsettling idea that the silence is deliberate. The zoo hypothesis suggests we're being observed, but not contacted, like animals in a cosmic wildlife preserve. More extreme versions imagine a dark forest universe, where everyone hides. If any civilization that reveals its location risks attack by others, natural selection would favor those who stay quiet and camouflage their presence. In such a cosmos, broadcasting your existence is like shouting in a dark, unknown jungle. These scenarios are speculative, and we have no evidence for hostile galactic predators. But they highlight a real question. Is it wise for us to announce ourselves with powerful radio beacons or laser messages? So far, humanity's loudest signals, like early television broadcasts and planetary radars, form a faint bubble only about 100 light-years wide. Most of the galaxy has never heard from us. Whether that changes is a decision we're still making. Ultimately, the Fermi Paradox forces us to confront our own significance. If the Great Filter is behind us, we might be one of the rarest phenomena in the universe, a technological civilization that made it through. That would make our future unimaginably precious. If the filter lies ahead, then understanding and surviving it becomes the central project of our species. And there's another possibility. Maybe there is no paradox at all. Maybe life is common, intelligence occasional, and galaxy-spanning empires a science fiction exception. The universe could be sprinkled with small, fragile civilizations, each briefly lighting up its corner of the sky before fading. We might be one of many, too far apart in space and time to ever meet. Right now, we simply don't know. Upcoming telescopes will study exoplanet atmospheres, searching for biosignatures like oxygen, methane, or industrial pollutants. We may soon learn whether life is common on other worlds, or eerily absent. Until then, the Fermi Paradox remains a mirror. When you ask, where is everybody? You're really asking, what are we, and how long will we last? As we keep listening to the quiet sky, Terra Nova will be here, exploring the mysteries of the universe with you.